Hi everyone and welcome back to my YouTube channel or the Big Structure Hub. This is a place where you learn, build and innovate. Today I want to talk about trapezoidal dam having water face vertically. And remember, in our last lesson or session, I talked about stresses across the base of the dam, and I never did an example concerning that session. So today I want to finish this topic of today so that we may tackle examples involving stresses across the dam and a trapezoidal dam having water face vertically, because it is the same thing for a rectangular dam and a trapezoidal dam. So let me finish this, then we will do more examples, including from past papers, that is Kenya National Examination Council, and so on. So stay tuned up to the end. So this is a trapezoidal dam. As you can see, it is in a trapezoidal shape, and this is a body of water. So from the name, water face vertically. So where the water is facing the wall of the dam is vertical. So the name come after the verticality of the wall of the dam. Sometimes you may find this wall inclined. So the water will be inclined. It will follow the shape of the dam. So for this case, it is following this shape of the dam, which is in vertically form. So I want to analyze this trapezoidal dam so that at the end of this lesson or session, you will be able to know how to calculate this force F acting on one side of the dam. Also, at the end of the session or lesson, you will be able to know how to calculate this centroid of pressure, which is from the base of the dam. Also, at the end of this session, you will be able to know the weight exerted by this masonry wall. And also, you'll be able to know the center of gravity of this dam from this side of the dam. Also, you'll be able to know how to calculate this distance x, which is the distance as a result of the resultant force cutting at the base at M. So the distance is nm. Also, you will be able to know how to calculate the stresses at this point A and also at B. Let H, this capital H, be the height of the dam. So from here to here is the height of the dam. And small h, this H, be the height of the water. And then A, from here to here, is the top width of the dam. And then you have B, from here to here, bottom width of dam. WO is the weight density of a dam masonry. And then you have small w, that's the weight density of water. And then the density of water is given by density of water times gravitational acceleration. So gravitational acceleration is always 9.81 meters per second square. So if you multiply the density of water, which is 1,000 times 9.81, you will get the weight density of water, which will be in Newton per meter. Then to convert to kilonewton per meter cubic, you will multiply by 10 raised to power negative 3, so that you will get 9.81 kilonewton per meter cubic. Then the force F, this force F is the force exerted by water. And then you have the capital W, this one is the weight of dam per meter length of dam. Now, let's start analyzing this dam. So I will begin by forces acting on the dam. So forces acting on the dam. So we have two forces, which is F. So F is given by small w times area times h bar. Remember, in our previous session, we talked about this. So our W times area. So area is base times h bar. So this one will be W times B. We consider one length of the dam. So times 1 times h over 2. So h bar is h over 2, which imply F is equal to W times h square over 2. So F is equal to WH. So F is equal to WH square over 2. So that is our F. And remember, this force F will be acting horizontally at a height of h over 3 small h above the baseline or above the base. So it is acting h over 3 above the base. After that, we will proceed to this W. So W, that is the weight of dam per meter length. So capital W, which is equal to weight of dam per meter length of dam. So this one will be the weight density, the weight density of masonry times area times length, like that. So the weight density of masonry will be, we said earlier that WO is the weight density of dam masonry. So this one will be W0 times the area. So the area will be the total area of this trapezoidal dam. So we know that the area of trapezium is a half into bracket the sum of two parallel line, which is B plus A. So A plus B, then you close the bracket, times H. So this is the capital H, times length is 1 meter. So this one will be W0 times A plus B over 2 times h. So that is the weight, of dam per meter length of dam. So that is how to calculate you calculate the weight of dam per meter length of dam. So this weight will be acting through the center of gravity of this dam. So this is the center of gravity. So this center of gravity is this distance AN. So we are supposed to come up with a formula that will help us to calculate this center of gravity AN, where our weight of dam W is acting. So let's see how we can come up with such a formula. So the center of gravity, the COG of weight, density of the dam per meter length. The center of gravity of weight density of the dam per meter length, this capital W, will be this distance AN. So to get the distance AN, you will first split the trapezium, this is the trapezium, into a rectangle and a triangle. As you can see, I have splitted so that I can have the rectangle and the triangle. Then you will calculate the area of this triangle, no, of this rectangle, times its centroid plus the area of this triangle times its centroid. Then you will equate to the area of the whole of this trapezium times its centroid, which is AN. So let me do it practically. So the area of rectangle is length times width. So that is A times B. No, A times H. Then times the centroid is A over 2 plus we come to this triangle. So the area will be a half base times height. So the base will be this distance from here to here. But since we have this distance from here to here as B and also from here to here as A, so our base will be B minus A, like that. Then times H, capital H. By doing so, we have calculated our area. Then times the centroid. The centroid will be starting from here. So it will be this distance A plus the centroid of this triangle will be B minus A, B minus A, so that we can get this distance from here to here. And then over 3 like that. And then we will equate to the area of this trapezium will be a half A plus B, A plus B times H times the centroid is A N, like that. So by doing so, you can simplify this expression and make AN the subject of the formula. So if you can make AN the subject of the formula, then you will get the formula which will help you to calculate this distance AN. This distance AN. But there is also a simplified expression the value of AN can also be calculated using this expression, whereby AN is equal to A square plus AB plus B square over 3 into bracket A plus B. So that this expression will help you to find the value of AN. So if this method, if this first method can be a problem to you, then use this expression to calculate the value of AN. Now we proceed to X, this distance from here to here. Now let X equal to distance, horizontal distance between the line of action of weight of dam and the point where the resultant force cuts the base. So this is the resultant force and it cuts the base at M. So it is very important to obtain this distance X. So in our previous analysis, we saw that to calculate the value of X, we use this formula, F over W times H over 3. This is small h over 3. After that, we proceed to eccentricity. Eccentricity, you know that eccentric is away from the center of an object. So for our case here, the center of this dam is at B over 2. And if we have a load W at point M, that one will be our eccentric load. So to get E, it means E is the distance from the center of this dam to where we have our eccentric load, which is W. So E will be D, this distance, minus B over 2, a half of the center of the dam. Also, you can obtain D, which is AN plus NM. D is very important because you will use it in the calculation of the stresses across the base of the dam. So we proceed to total stresses across the base of the dam. So total stresses at point B will have the maximum stress, which is equal to W over B plus 6WE over B square. So this formula is the same as the one we derived in the rectangular dam. Also, stresses at point A. So at point A, it will be the minimum stresses at the base of the dam. And this is calculated using this formula, W over B minus 6WE over B square. So that marks the end of trapezoidal dam having water face vertically. So in my next session, I will be tackling examples regarding this topic, and I will begin by a question from past paper, that is NEC, Kenya National Examination Council, Module 2. So stay tuned for more